Imagine asking an AI to, code a fully working interactive multiplayer video game totally from scratch.
Right.
And it actually finishes generating the entire code base before you can even lift your finger off the enter key.
Which is just wild to think about.
Under 2 seconds.
Yeah,
I
right.
mean, it's mind-blowing. Welcome to the Deep Dive. Today we are bringing you a massive stack of technical research to explore a total paradigm shift happening right now in the tech world.
Yeah, it's a huge pivot.
It really is. For the last few years, the entire industry has been running this single marathon focused entirely on raw intelligence, right? Labs were just stacking up parameters, feeding in more data, trying to get models to pass the bar exam.
Exactly.
But if you look at what the top engineers are actually doing today, that marathon has suddenly turned into a drag race. The race for intelligence is transforming into a race for pure, unadulterated speed.
It is, yeah. The landscape is undergoing this truly fascinating pivot because when you look at the recent benchmarks, the intelligence gap between open source models and closed source models, it's rapidly converging.
Right, they're all catching up to each other.
Exactly. We are hitting this plateau where raw intelligence is no longer the sole differentiator. So the new frontier, the metric that will absolutely separate the winners from the losers, is how fast you can deliver that intelligence to the user.
And getting to that sub-second delivery speed, I mean, that requires completely dismantling the way we currently process data, doesn't it?
It absolutely does.
Well, that is our mission for today. We're going to unpack exactly why large language models have historically been so notoriously slow.
So slow, yeah.
We'll explore a radical hardware breakthrough that solves this by essentially defying traditional physics and look at why blazing fast inference fundamentally rewrites the playbook for how the developers and builders listening to this right now will actually architect software and AI agents moving forward.
It's going to change everything about how we build.
But before we talk about how to achieve those crazy speeds, we really need to isolate the bottleneck. Because I think the instinct is to just assume these massive server farms are bottlenecked by complex equations, right? Like the processors just can't calculate the math fast enough.
Yeah, and that is actually the most common misconception. The processors themselves are incredibly fast at executing the math.
Okay.
The actual constraint on LLM inference is data movement.
Interesting.
To understand why, you have to look at the mechanics of token-by-token generation in a transformer model. The architecture is autoregressive, which means it generates one word or token at a time.
Right. One word after another.
Exactly. So to predict that single next token, the input has to pass through all the transformer layers via massive matrix multiplications.
Okay, so a ton of math for every single word.
Right, but it means the entire massive file containing the model's weights has to physically travel from the memory chips over to the compute units for every single word generated.
Okay, let's unpack this because this is crucial. Imagine you have a master chef who can chop vegetables at lightning speed. Their knife skills are unmatched, and that represents our compute processors.
Okay, I like this.
But their pantry is located in a warehouse entirely across town.
Right.
So for every single grain of rice, for every pinch of salt, they have to drive across town, grab it, drive back to the kitchen, and add it to the pot. That is essentially the GPU data commute.
That's a perfect way to visualize it.
The chef isn't slow at all. The commute is slow.
Oh, and the technical term for that commute is the von Neumann bottleneck. If you look at a standard GPU, which is, the industry workhorse right now, the physical design actively separates compute from memory.
Because of they're built, right?
Exactly. Because of traditional manufacturing processes where silicon wafers are cut into these smaller chips, a GPU only has a tiny amount of on-chip memory. We're talking maybe 80 to 100 megabytes.
Which is nothing compared to the size of these models.
Exactly. These massive language models can be hundreds of gigabytes, so they have to be stored off chip in what's called high bandwidth memory, or HBM. And this creates a severe memory wall.
A wall that just stops everything in its tracks.
Right, because the off-chip bandwidth is limited to roughly 8 to 1.6 terabytes per second. So the GPU cores just sit there idle, literally waiting for the data to make that physical journey across the circuit board.
And I mean, that latency might be somewhat acceptable if you just want to generate a quick email template or something.
Sure, yeah.
But when we look at modern reasoning workflows, where an agent is planning, breaking down complex problems, running self-correction loops, or even deliberating with other AI agents.
Right, those complex agentic loops.
Yeah, those systems require hundreds or thousands of sequential generations, so that data commute latency compounds disastrously.
It makes autonomous agents practically unusable for real-time tasks. Like, think about it. If your multi-agent system needs 50 back-and-forth steps to resolve a single coding error, and each step carries a 5-second data commute penalty, you're waiting minutes just for a simple resolution.
Right.
The system physically cannot operate at the speed of thought.
So if the chip-to-chip connection is the real bottleneck here, it begs the question of why we are still manufacturing processors this way at all. I mean, the solution seems to be avoiding the commute entirely by just stopping the practice of cutting the silicon chips into tiny squares.
And what's truly fascinating here is how a company called Cerebras decided to attack that exact manufacturing constraint.
I was hoping we'd get to them.
Yeah, in traditional fabrication, you take a massive 12-inch circular wafer of silicon and you cut it into dozens of smaller chips. Because microscopic defects in the silicon are inevitable.
Like a speck of dust or something?
Exactly. If a piece of dust ruins a millimeter of the wafer, you just throw away that one little square. But Cerebras completely reimagined this with their Wafer-Scale Engine 3. They basically keep the entire silicon wafer intact.
Wait, but how do they handle the inevitable manufacturing defects if they aren't throwing away the bad parts? I mean, you said dust is inevitable.
Right, so they build redundancy directly into the hardware logic itself. They bake extra cores into the wafer, and they've developed this incredible communication fabric that simply routes the data path around any microscopic dead zones to a spare core.
Oh, wow. So if a core is dead, the traffic just takes a detour.
Exactly. And the result is a single massive continuous chip that is roughly 58 times larger than a standard GPU.
A single processor the size of a dinner plate.
Literally, yes. A single processor housing 900,000 AI-optimized compute cores.
That is just staggering.
But the real breakthrough is the memory. Because they have so much continuous silicon, they can fit 44 gigabytes of on-chip SRAM.
And SRAM is the hyperfast stuff, right?
Right. SRAM is etched directly next to the logic gates, unlike that HBM, which sits further away. This means that for a vast number of models, the weights can be stored directly next to the compute units.
So they basically move the pantry directly into the kitchen.
Perfectly said. The data commute is reduced to roughly 0.1 millimeters. And because the data barely moves, they can push the memory bandwidth to an astonishing 21,000 terabytes per second.
21,000.
Yeah, which is roughly a 2,600 times increase compared to a standard GPU.
Okay, here's where it gets really interesting, though. If the weights absolutely have to stay resident on this one giant chip to achieve these crazy speeds, what happens when a model is just too massive?
Like a really huge frontier model.
Yeah, say a 70 billion parameter model that requires way more than that 44 gigabytes of memory. Does this entire dinner plate architecture just hit a wall?
It's a great question, but the architecture is actually designed to handle that through something called layer boundary splitting.
Okay, how does that work?
Well, in a transformer model, layer 2 doesn't need to do any math until layer 1 is completely finished.
Right, it's sequential.
Exactly. So for massive models that exceed the capacity of a single wafer, the model is simply sliced at those layer boundaries. You place layers 1 through 10 on wafer A and layers 11 through 20 on wafer B.
Ah, I see.
The massive weights stay permanently resident on their respective wafers. They never move. The only thing that travels across the wire between the different wafers is the resulting token, the tiny activation data.
So you preserve the extreme speed because you never reintroduce that massive weight commute. You're just sending the final chopped vegetable over to the next chef.
Exactly. And that physical pipeline fundamentally changes how traffic is managed, too.
Right, because on a standard GPU, pulling the weights from memory is so painfully expensive. Systems try to maximize throughput by batching hundreds of users together, don't they?
They do, yeah.
They make everyone wait in line until there's a big enough group to justify the massive data commute.
Which adds to the latency you experience as a user. But on a wafer-scale engine, because the weights stay put and the tokens flow through the layers physically, you can actually have concurrent users occupying different physical layers of the chip at the exact same time without that traditional batching.
So user 1's token is being processed at layer 3,
Yeah.
while user 2's token is already entering layer 1.
Exactly. It allows for continuous flow, which translates into those ultra-fast inference speeds. We are talking up to 1,780 tokens per second.
That is just, it's hard to even wrap your head around that speed.
It is. But the hardware is really only half the story here, because that extreme inference speed forces a major engineering shift that dictates the actual shape of the code developers write.
Right. It changes the software itself.
Yeah, there is a concept emerging in the sources called the 500 millisecond threshold.
Okay, tell me about that. Because when an AI can reliably process complex logic
Yeah.
and respond in under half a second, the entire architecture of a web application fundamentally changes, right?
Totally.
Like, think about the slow path we are all so used to building today. When an API call to a model takes 3, 5, or even 10 seconds, developers are forced to build these massive, brittle, asynchronous machines.
Oh, the asynchronous overhead is awful.
You have to set up message queues, run background worker threads, continuously pull the server for status updates, manage complex job states just in case the user closes their browser while the AI is quote-unquote thinking.
Yeah, and for the user, it just means staring at a spinning loader that says generating for 10 seconds.
Right. But when response times drop below 500 milliseconds, developers can completely delete all of that asynchronous orchestration machinery.
Just wipe it out.
You replace it with a simple synchronous function call. The front end requests the data, the thread blocks for a fraction of a second, the data arrives, and the page renders. There is no polling. There are no background workers. And there is absolutely no spinner.
It's beautiful. If we connect this to the bigger picture, it really is like the shift from 1G to 5G cellular networks.
Oh, that's a good analogy.
Yeah, jumping to 5G didn't just make loading web pages faster, it unlocked entirely new business models like Uber and mobile video streaming that were physically impossible before.
Right.
And in the same way, removing that asynchronous overhead in AI unlocks entirely new categories of applications. You can build real-time voice agents that converse without those awkward 3-second pauses.
Which we've all experienced and hated.
Exactly. Or you can build live translation tools that parse and translate syntax fluidly while the speaker is literally mid-sentence.
That's incredible. And the sources actually highlight a benchmark that perfectly illustrates this shift. They ran a 4-step customer support workflow.
Oh, yeah, this is a great example.
So the AI has to classify an incoming issue, summarize the context, draft a reply, and then write an internal follow-up log.
4 distinct LLM calls.
Exactly. And on a traditional GPU setup, that 4-step chain takes 6 to 7.2 seconds. It forces the human customer service agent to just sit there and wait.
Right, twiddling their thumbs.
But on the Wafer-Scale engine, that entire sequence completes in 1.5 to 3.5 seconds. The AI finishes the entire analytical workflow before the human agent even has time to refocus their eyes on the screen.
It's basically instant from a human perspective.
Right.
And, the HTML pool game test in the sources is even more illustrative of this threshold.
Oh, I loved this part. Tell them about the pool game.
So the researchers prompted 2 different setups to write a complete, working 2-player HTML pool game entirely from scratch, using a 4,000 token budget.
Okay.
They pitted the massive GPT-OS 120B model running on Cerebras against a much smaller GPT 4.1 mini model running on a standard GPU.
And conventional wisdom says the smaller model should be snappier, right? It's lighter.
Right, that's what you would assume. But the massive 120 billion parameter model on Cerebras finished generating the entire game code base in about 1.95 seconds.
Under 2 seconds for a full game.
Yeah. And the smaller model on the GPU took roughly a minute.
Wow.
So when you slash a minute of wait time down to under 2 seconds for a massive context generation, generating and rendering interactive applications completely on the fly becomes a practical reality.
Let's actually apply that to something like real-time web personalization.
Yeah.
Because historically, personalizing a web experience was an asynchronous, offline process, right?
Very much so.
Marketing teams would run batch jobs overnight, store the recommendations in a massive database, and then serve them the next day. The data was often stale, and it was super limited to pre-computed categories.
Yeah, you only fit into bucket A, B, or C.
But with sub-second inference, that personalization moves directly into the live user session. A user lands on a web page, and in the fraction of a second before the DOM even renders in their browser, the AI executes complex personalization logic.
And to make this work without the AI hallucinating or just generating annoying conversational filler, like, sure, I can help you with that, developers are using strict pydantic schemas.
Right, so we aren't just crossing our fingers and hoping the AI replies with good text.
Exactly. Pydantic schemas enforce a strict data contract. Instead of asking the AI to simply write a personalized welcome message, which, might result in the AI politely introducing itself first, you pass the model a rigid JSON template.
You force its hand.
You absolutely do. It forces the AI to only output a specific key value pair. So you combine a static activity scenario, like showing a tourist activity in New York, with a dynamic visitor profile containing the user's specific real-time preferences.
Okay.
And the AI instantly outputs a JSON object containing a custom hero title, tailored copy, and even a rationale explaining why it chose that phrasing, all of which maps straight into the React components on the front end.
In literally less than a second.
Yes.
Taking that concept of real-time processing into high-stakes workflows is really where the architecture shines, though. The sources detail this real-time investment capstone project.
That project is fascinating.
It really is. It's a system designed to fuse LLMs with instant non-LLM tools like local database lookups.
Yeah, it basically serves as a blueprint for a real-time agentic router. Imagine an autonomous agent ingesting a continuous live stream of market signals, like breaking press releases and financial tweets.
Okay, that sounds like a lot of noise.
It is a ton of noise. And as each signal arrives, the system has to decide instantly whether to act on it. So to maintain high responsiveness, it uses a hyperfast initial classifier to route the signal down one of 4 distinct paths.
Right. And the first path is just ignore, right? If the news is irrelevant, the system drops it immediately to save compute.
Exactly, filter out the noise.
The second is quick update. So if the news reinforces the existing investment strategy, the system does a lightning-fast SQLite database lookup, extracts the new facts, and updates the state without heavy processing.
Very lightweight.
Then the third is factor fresh, which triggers when there are new facts but maybe no obvious stance change, prompting a slightly deeper review. And the fourth is full review, which is triggered by negative, highly volatile, or just mixed news. So what does this all mean for system safety? I mean, I have to challenge this architecture a bit here for our listeners.
Go for it.
If I'm building an autonomous finance agent, letting a hallucination-prone language model make a split-second buy or sell decision based on some random press release sounds like an absolute recipe for a catastrophic flash crash.
And that is a very critical concern. But it is exactly why the router is designed as an orchestrator, not a single decider.
Okay, explain that.
The fast split-second model isn't actually making the trade, it's classifying the risk. By relying on those strict schemas and selective deep dives, only the truly safe, redundant signals get pushed through that quick update path.
Oh, I see.
The moment the router detects risky, novel, or negative news, it forces that full review path, and that path intentionally dynamically slows down the entire system.
It pumps the brakes.
Exactly. It runs a full suite of analytical tools, pulling historical data, comparing risks explicitly, and it likely loops in a heavier, more methodical model before any action is ever taken. By classifying first and acting second, the agent only works as fast and takes as much risk as the specific data profile allows.
Okay, so you are essentially building dynamic speed limits into the routing logic itself.
Precisely.
That's brilliant. But if the AI is moving fast enough to execute these multi-step actions in seconds, I mean, human developers can no longer afford to code or manage systems the way they used to.
No, the whole developer playbook has to evolve. In an era where models output 1,000+ tokens per second, the human role shifts from being a manual coder writing every single line to being a high-level orchestrator managing fleets of these microagents.
And the orchestration pattern outlined in the sources suggests pairing different models for different cognitive phases, doesn't it?
It does. You essentially act as a manager delegating to a senior architect and a junior executor. You use a highly intelligent but much slower model like Codex, for example, which might run at 80 tokens per second but has a massive 400,000 token context window. You use that to plan the blueprint and evaluate the overall logic.
So that's the senior architect taking their time to design the house.
Exactly. Then you hand the actual step-by-step checklist execution over to a hyperfast model like Spark, running at 1,200 tokens per second.
A junior executor with a nail gun.
Exactly. But because that executor model is streaming code blindingly fast, you have to establish really strict workflow guardrails.
Right.
You are essentially managing a hyperactive intern who types at 1,000 words a minute. If you aren't absolutely deliberate about scoping their permissions, they will confidently write terrible code, or worse, execute a completely destructive command before you can even hit Control-C to stop them.
Which is terrifying. And the sources outline some non-negotiable guardrails for handling this kind of speed. For one, you have to enforce maximum diff sizes. You keep code changes under 150 lines, or even under 30 lines, unless it's explicitly requested. You also absolutely have to ban dangerous terminal commands at the system level.
You cannot rely on the AI to just know better.
Right. Commands like arm-rf cannot be allowed because a fast agent trying to just clean up a directory might wipe your entire production database in half a second.
Yeah, that would be a very bad day. But while the speed requires those strict guardrails, it also grants developers incredible new
Oh,
capabilities.
for sure.
Like quality control checks that used to feel way too tedious or just too slow to run constantly, they are now practically free.
Yeah.
You can configure the system to run the full test suite and do all the type checks automatically between every single micro task.
Because it only takes a fraction of a second.
Exactly. Furthermore, you can embrace aggressive cherry picking.
What do you mean by that?
Well, with slow models, developers often wait a few minutes for a UI layout and then they just accept whatever it outputs because they really don't want to sit and wait for a regeneration.
Oh, yeah, the good enough compromise.
Right. But with a fast model, you can request 15 completely different UI variants in a single minute, review them all visually, and just pick the best one.
That's a total game changer for front-end design. But this raises an important question about memory, though.
Okay, yeah.
If an executor model is running at 1,200 tokens per second, it is going to chew through its context limit incredibly rapidly. You could fill up a 128K context window in a matter of minutes.
Yeah.
Doesn't the model just lose the plot and forget what it was even doing?
Yeah, that is the profound danger of context compaction. It is
Yeah.
very similar to asking someone to memorize a deck of flashcards being flipped in front of their eyes at 10 frames a second.
Right, you're going to miss a lot.
Eventually, the older cards just get blurred together or completely dropped so the brain can hold on to the new ones. The sources note that once an LLM crosses roughly 80% of its context capacity, compaction and degradation are mathematically guaranteed.
It's unavoidable.
Completely. The attention mechanism dilutes, the model forgets its earlier constraints, and it just starts drifting from the original plan.
So we can't just keep hitting the clear button and making the AI start from scratch, right? The solution detailed in the sources is externalizing memory through a strict four-file system.
This is such a clever approach.
It really is. Instead of relying on the AI's internal ephemeral context window to remember the state of the whole project, you force the system to maintain 4 permanent markdown files directly in the local directory.
Yeah, the structure is so elegant. You have agents.md, which stores the repository norms, formatting rules, and strict operational boundaries.
Basically the rulebook.
Right. Then you have plan.md, which is the overarching blueprint and step-by-step checklist generated by that slower architect model.
Okay.
You maintain progress.md, which acts as a running log of what has actually been completed so far. And finally, verify.y.md, which contains the terminal commands required to prove the code actually works.
So every time you spin up a fast agent to execute a bounded microtask, it starts with a completely clean slate.
A fresh brain.
Exactly. It doesn't drag a massive, messy chat history along with it. It just reads those 4 files, executes the very next item on the plan, updates the progress file, and then completely shuts down.
Right. The state is maintained in the file system itself, not in the LLM's memory.
It keeps the fast executor sharp, precise, and just hyper-focused step after step.
It really represents the ultimate workflow pattern for this new era of ultra-fast inference. The architect plans the state, the executor acts on a small bounded step, and the state is immediately handed back to the file system.
Wow. Let's take a breath and just recap the incredible journey we've mapped out today. We started by isolating the physical limitation of AI inference, the von Neumann bottleneck, right? Where the data commute of massive weights traveling across circuit boards severely constrained how fast these models could operate.
Right, the chef driving across town, and then we explored how wafer-scale engineering eliminated that commute entirely.
By not cutting the silicon.
Exactly. By keeping the silicon wafer intact and building redundancy logic to route around those microscopic defects, they move the memory directly next to the compute. And that unlocks bandwidths that shrink processing times from minutes down to milliseconds.
Which pushed us past that 500 millisecond threshold, completely deleting the need for asynchronous code architectures, spinning loaders, and complex background workers.
Say goodbye to the spinner.
Seriously.
Yeah.
And that speed enables real-time agentic routing, instantaneous web personalization via strict data schemas, and ultimately forces software engineers to evolve into high-level AI orchestrators managing bounded microagents through externalized memory.
We are truly watching a fundamental shift in computing history. Faster hardware doesn't just optimize old tasks, it dictates entirely new software architecture, which in turn enables entirely new categories of applications. AI is transitioning from a slow oracle that we query to an engine that executes logic continuously alongside us.
Which leaves me with a final thought for you to chew on. As inference latency approaches absolute zero, right, As the hardware and the software architectures tighten, we are going to stop treating AI as an external tool we have to wait for.
Yeah, the wait time is disappearing.
So, if an AI system can process complex logic, root decisions, write code, and render a user interface exactly as fast as your own internal monologue, at what point does using AI stop feeling like operating a machine and start feeling like a literal physical extension of your own cognitive processing?
Man, that is a profound threshold to cross, and we are accelerating toward it every single day.
We really are. Thank you for joining us on this deep dive. Take some time to reflect on all the architectural shifts we unpacked today and ask yourself, with latency totally out of the equation, what real-time application would you build first? Catch you next time.